We might as well get started. You can see from the title slide that we are starting our discussion of multitasking, which is a central and very important component of any modern operating system. If you think about an operating system managing resources and allocating resources to processes or programs that you're running, the most important resource of all is the processor. So, of course, we need a way of reasoning about that. We need a way of implementing that and enforcing all of the various constraints. We talked about this some. Having protected mode is really important so that we can maintain isolation between processes, but also having a hardware timer that only the kernel can configure is of essential importance to make sure that programs will eventually release the CPU to someone else. So that becomes extremely important for reliability and also for, just making sure that programs don't have to think very carefully about how they're written. Okay, let me see. I see an unrelated question. Are we supposed to upload the design doc on Canvas on top of committing it to your repo? Yes. The answer for that is yes. And I realize there's some redundancy. CS130 doesn't have this redundancy because I was able to learn from 124, but we haven't updated the CS124 process. There will be a difference between what you put in your repository and what we see on Canvas, which is your commit hash. That'll be the commit that we extract, and we will grade that specific version. So you could have like horrible versions all the way up and horrible versions all the way after. We'll grade that one version. So that's part of why we want you to submit that. In fact, I mean, that's what we did in 130 is we just had you include the commit hash and how many late tokens. But for now, we'll just have the entire design document submitted on Canvas as well. Okay, so if you have any other logistical questions that come up, let me know. I'll try to fit them into the sequence, the flow, without disrupting things too much. But the concept of a process, you've probably heard this term a lot. I hope you have, and I hope you're used to using it. But a process, the way that people normally describe this is a process is a program in execution. And I like to think of it as a recipe. I know there are some cooks in the audience, and if you think about a recipe being a program, a process would be equivalent to you marking off the steps you've completed and where you are in the recipe, and your layout, your mise en place on the countertop, what you've done, the bowls, everything that's ready, stuff that's in the oven, the timer that ticks, and dings when the oven is done, and all of this kind of stuff. That would be the process because you're in the midst of executing that recipe. So I think that's a great analogy. You can see that on the slide we talk about sequential processes. Processes tend to be sequential, execution flows. We don't really talk about parallel execution flows in the context of a process. Now, you may be scratching your head and saying, well, what about threads? What about multi-core? Yes, we'll talk about that in a future discussion. But in this point in time, you can think of a process as being a single flow of execution through a program, okay? And so we use processes, we manage processes, we switch between processes, we have ways of interrupting processes and resuming processes, and that's how we implement multitasking in modern operating system implementations. So here's what's normally in a process. You can see the program instructions. Strangely enough, we call this the program text. This is a historical term, and it certainly, you could look back at punch cards, and punch cards were done in a very limited character set. It tended to be a 7-byte character set or an 7-bit character set or an 8-bit character set, depending on the computer. So program text, now it's binary, and you dare not try to print it to the console because it may mess up your terminal. And you have to reset your terminal just to get it to act normal again. But you can see the CPU state, so the registers, the program counter, flags, and so forth. And you can see the other things. We're going to talk about that quite a bit today. So the OS has this important role of managing the processes. And part of this is time multiplexing the processor so that every process gets a go. And there's various ways that you can construct that. We talked about cooperative multitasking, where processes voluntarily relinquish the CPU, and also preemptive multitasking, where the OS is capable of kicking a program off of the CPU. And we prefer preemptive multitasking. That's what you will implement in Pintos, or I should say that's what's already implemented in Pintos, and you will extend it. Okay. We'll talk briefly about the process lifecycle. There's a typical state diagram that you'll see in systems texts that describe the process lifecycle, and it captures pretty much all of the important states. So you have to create a process. Fork is the thing that we've all been using. That's kind of the Unix mechanism, and it's a simple mechanism. You don't have a notion really of starting a process from scratch in Unix, but you definitely do in Windows. You can start up a process and tell it what program to run. It's not a fork of a parent or anything like that. So it's kind of an interesting thing how different operating systems have different approaches. And if you're interested in looking into this, I'll just tell you, Google fork is broken. And there's a lot of interesting discussion about whether or not the Unix process abstraction is even a good one. But it's definitely one that's worked well enough for many years now. So you create a process. Yeah, so here's some examples created by the operating system at startup, created when the user invokes a program via command shell or double-clicking on something in the graphical user interface, or when processes spawn other processes. There is one process at the very beginning that's started up by the kernel bootstrap mechanism. And so that'll be the ancestor of all other processes in Unix. Used to be called init. Now in Linux, it's called systemd. If you're on a Mac, there's something called launched that is the ancestor of all other processes. So that's the thing that started by the kernel bootstrap at the very end, once everything else has been initialized. Okay, so you have a set of processes. You consider all the processes that your OS knows about and is managing. There will be some of them that are trying to read from a file. There will be some that are reading from the keyboard, waiting for the user to do something, or waiting for a mouse to do something. I got my mouse right here. So you have these different steps that a program could be in, and if they had the processor, they couldn't do anything because they're waiting. They're stuck. They're waiting for data to show up. And so the rest of the processes that could make progress if they had a CPU are described as being ready to run. And so we have another state here. Let me see if, yeah. So you have ready to run processes, and one of those per CPU is actually on the CPU. Okay. So that's what we mean when we say a process is running. It has a CPU, it's making progress, and it's not blocked on anything. Okay, then you have the rest of those processes that could make progress if they had a CPU, but we may have many more ready processes than CPUs. So those will be in a collection in the ready state. Okay. Now, when you create a new process, obviously the one that created the process is currently running on the CPU, so it trapped into the kernel to start a new process. And so the new process immediately goes into the ready state because we don't know when it should run next. There's prioritizations, there's other things that go into figuring out who gets the CPU next. And so the OS will allow the running process to be on the CPU for a certain period of time. Various things can kick it off. We'll talk about this. If the program continues to run and it completely uses up its time slice, then the OS will kick it off of the CPU and move it back into the collection of ready processes. And then it will pick someone else, and it's their turn to get the CPU. So this is the whole notion of scheduling. The scheduler is the thing that picks a process from the collection of ready processes based on some design criteria of the operating system implementation. You have prioritization, like the thing that responds to the mouse or the thing that plays back music tends to be a very high priority, and other things that are very compute intensive and will use the CPU as long as they can tend to be low priority. We'll talk about this a lot in the future. Now, what if a program does, it's on the CPU and then it does decide to read from the disk or read from the network, or read from the keyboard or something else that's slow, and there's no data. What happens in that situation? Well, the OS knows that that program can no longer make progress. And so what it does is it moves the process into a blocked state. Now, you can imagine there's many kinds of substates of blocked processes, and we'll talk more about that today. But the process basically becomes blocked until the resource becomes available, okay? And so the kernel doesn't make everybody wait. It just moves that process into some other collection, and then it goes and grabs another ready process based on some criteria and puts that on the CPU to run, okay? So it's a really clever mechanism. It's a pretty straightforward mechanism. I feel like it makes sense. Let's say that disk operation completes. So the kernel talks to the disk controller on behalf of the process and says, hey, can you read this block from this part of this storage device? And the disk controller gets set on it. And when the disk controller finishes, it raises a hardware interrupt. So that causes an interrupt to occur in the kernel. We interrupt out of whatever process was running. The kernel finds out and it says, this process was waiting for this block of data. So now it can move it from that blocked state into the ready state again, so that eventually it will get the processor, it will have its data, it will be able to make more progress. Now, eventually, a process will terminate. It may be seconds, especially if it's buggy or if it just has a very simple task that it needs to complete. But it's not uncommon in Unix systems to have processes running for months, if you happen to have a system with good uptime. But it eventually will terminate. Now, there are certain things that have to happen when the process terminates. And so we call these exit handlers or add exit tasks, things like that. Not only that, but the kernel has to reclaim any resources that the process is still holding when it terminates. Many of you have encountered the difficulty with the command shell, like, oh, I've got to close this, I've got to close that, I got to close this. But I don't know if you've thought about the fact that you don't manage closing standard in. You don't manage closing standard out. And if standard out is redirected to a file, well, who manages flushing and closing that file? The kernel takes care of it for you. And so there's certain termination tasks that have to occur when a process is being terminated. And so that's why we go from running to terminated. That sort of goes straight, you end up in the kernel, the process is cleaned up, and then the kernel goes back, finds another ready process, and selects it to run on the CPU. There are multiple reasons why a process may terminate. You could probably enumerate several. One is voluntary termination. So the process itself says, I'm done running. So it calls exit, or maybe it calls abort. Some of you have looked at using abort for signaling error conditions and so forth. Maybe it returns from main. The way that the kernel sets up a process is as if the return value from main is passed directly to exit. So even if you don't exit in your program, exit gets called eventually. Okay, and the status, the exit status of the program is recorded by the kernel so that other processes can query it. You may have involuntary termination because there was a fault. You dereferenced null, or you made a garbage pointer and then tried to do stuff with it, and eventually something horrible happened and the OS said, that's it, I got to step in. You may have a signal sent to a process from another process. I have this happen rather frequently, especially when I'm doing development. I'm on macOS Big Sur. I don't know if any of you have upgraded to Big Sur. If you haven't, I would say don't until you absolutely have to. I've run into a lot of difficult problems with Big Sur, and sometimes I have processes that hang and I have to switch to a command shell and kill them to get them to stop. Kick them off the processor and off of the ready queues. So it's kind of frustrating. This state diagram covers most of what you need. In fact, I think that this probably completely captures the Pintos process sequence that you might ever encounter in your PINTOS assignments. But there are a few additional states that are incorporated for the sake of achieving more advanced goals. So one of them is the ability to suspend and resume processes. What does that mean? Well, when we suspend a process, we don't really care if it could run on a CPU, if it had a CPU. We don't care if it's blocked. What we're basically saying is, I don't want to schedule this process at all right now. So you're basically taking it out of the program scheduling for a certain period of time. And so we may move a process from ready to ready suspended because it could run, but we don't want to. We want to just pull it out of the ability to schedule it. If you hit Control Z in a command shell while a program is running, you may see that suspended message, and then you know that you can type FG to resume it in the foreground, or BG if you want to resume it in the background, or if you do this to multiple processes, you can type jobs and it'll show you all the suspended processes. So I don't know how many of you have tinkered with this kind of thing, but you are moving processes into the suspended state and then back out of the suspended state when you do those kinds of things at the command shell. Same thing if you do ampersand, that'll run it in the background, but if it does any kind of IO with the console, it will suspend because now, something else is using the console, so it'll actually suspend. There's a lot of interesting nuance around that you may or may not be aware of. Now, if a process was running and it performed a long-running operation, it's reading from the console, it is reading from the disk, and you decide to suspend it, then we can move it into a blocked suspended state because it's blocked, and we need to keep track of the fact that it's blocked as well as being suspended. And of course, if the long-running task completes in the background, then it can be moved from blocked suspended to ready suspended. Okay, so this is the final process lifecycle. This captures just about all the kinds of things we may need to be aware of in implementing a process abstraction for an operating system. Okay. Now I want to ask if there are any questions about how this works or any questions about the details here. If you have any, feel free to pipe up or plop them in the chat. But I wanted to mention a few specific questions as far as implementation is concerned, things we have to think about. Okay, one, of course, is how the process's resources are managed and reclaimed. We need to keep track of them somehow. And what you'll notice as you get into PINTOS is there's a lot of stuff to keep track of. And that's kind of why I say OSs are really just sophisticated bookkeeping programs. The only complexity comes from the fact that you're talking to hardware and the fact that a lot of stuff can interrupt a lot of other stuff. So that's really what makes operating systems complicated to implement. How are block processes managed by the OS? We'll talk about that today as well. How do we switch what process is currently running? Hopefully, in courses like CS124, you've heard of this concept of a context switch. I know that I've mentioned it and I've spent a little bit of time talking about it. We are going to increasingly dive into how context switches work as we get into the nitty-gritty details of OS implementation. We'll start talking about it today. And then the big question, which is how does the OS choose what process should run next? Okay, and that's the problem of process scheduling. You can imagine that we may want to optimize for a lot of different things. I mentioned my mouse sitting right here on my desk. Well, when I move my mouse, even if the computer's doing something else, I'd like my OS to interrupt that stuff and react to my mouse so that I don't get frustrated as a user. And maybe some of you, especially now that we're all working remotely, working on a command shell where you're SSH'd into a remote computer and you type, and it takes a little time for the remote terminal to, or the remote connection to respond to the things that you type, it can get really irritating. So there's different things we can optimize for when we schedule processes. Here is a sort of a classical example of the information that we want to keep track of for a given process. You'll notice we call it a process control block in this discussion. I think that's a BSD term, really, when it comes down to it. It has a lot of other names, and if you happen to dive into Linux internals, you would see it talk about a task struct. Task structs correspond to both processes and threads in Linux because threads in programs are also managed by the kernel. So here's a representative example, color-coded so that you can see that these things fall into different categories, but we'll go through these various details as we go through the next few slides. It's pretty straightforward. You'll see all of these things represented in some form or another in Pintos. Okay, process identification. Number one thing is we need a way to refer to processes. In Windows, that would be some kind of handle, because that is classically the way that the Windows API works, is you have handles for all kinds of things. The way that it works on Unix is through a process ID, or a PID, as it's frequently called. So we need to somehow map that process ID to the information for the process. And there's a lot of different ways it can be done. Linux happens to use a hash table because we assume that this is not going to be densely populated. It doesn't make sense to have a computer system with 1 million processes running. That's going to be prohibitively slow for many different reasons. We may have hundreds of processes. We may even have thousands of processes if you're talking about managing individual threads of execution as well. So that's not too bad. And we can typically use some kind of hashing structure to map process IDs to the actual process details themselves. Okay, and you'll see this kind of thing in Pintos. I'm trying to remember. I think a lot of it is actually done through linked lists, but I can't remember all of the details. I'll have to look at it. It's been a year since I looked at the Pintos sources, as you can probably guess. Another aspect of what is tracked for processes is whether or not there's any kind of hierarchy information about processes. Unix in particular has this abstraction. Windows, not so much. And so you'll definitely see this in Unix, and you'll see it in Pintos, because Pintos follows a Unix model. But you always know your parent. The reason why is because you can actually ask for your parent process ID. So it's get ppid will tell you your parent process ID. And you also know all your children. And part of the reason why you know your children is that you have a special relationship with your children in the process abstraction. Child processes, when they terminate, will notify the parent that they've terminated. And so that's one of the things that you will get to implement in Pintos. And parents are allowed to wait on their children. They're not generally allowed to wait on other processes, except in very special circumstances. You can use wait to ask if another process is running, but that's about the extent of it. And that's why, Project One, when you read the description, talks about some of the limitations, why you have to construct a command shell in a particular manner, because there's a special relationship only between parents and children in Unix process abstractions. Okay, so every process has a parent, blah, blah, blah. I mentioned init here. I should probably mention something. So I mentioned the ancestor process. Used to be init. On Linux, it's systemd now. On Macs, it's launched. And there's various other example ancestor processes. When a child outlives its parent, it still needs to have a parent. So the OS kernel will go ahead and reassign that process to be a child of the ancestor process. The ancestor has a number of roles. One of them is to clean up orphaned processes when they terminate. So that's one of the things that happens. Process will have 0 more children, and also know what process group it's in. So a process can start a group, and then child processes will automatically be part of that group, and you can send signals to the entire group of processes. That's another part of the Unix abstraction. It's like I was saying, not every OS abstraction provides this mechanism, and Windows is a notable example where the processes are all pretty much peers of each other, as opposed to having a parent-child type of relationship. Is one right and one wrong? Not really. It's just different mechanisms. And you could explore any number of abstractions in your own OS implementations if you wanted to. And that's one of the things that I like about OS research is trying to think of novel ways of having processes interact and collaborate, because it's a very common approach. Many of you are probably aware of the Postgres database server, and it is implemented using entirely processes. Part of the reason why is because it was written a long time ago when not every OS had kernel thread support. And so they decided to construct that database to only use processes that collaborate with each other. There's very sophisticated things you can do. So it's interesting to think about what OS abstractions you might expose if you're doing your own OS implementation from the ground up. Okay, process state. So this is going to capture what we call the process's context. So remember, process is a program in execution. So this is all the details of where we are in the program, what's the register state, what's the flag state, what is the memory state, what other resources do I have open right now, what files do I have open, what network sockets do I have open, what pipes. All of these kinds of things are recorded in the state vector. So you can see that we know information about the CPU. So programs can be run with different prioritizations. They can be run with different permissions or privileges. And so a lot of that information will be captured in the CPU state as well. Processor. So one of the interesting things about running a program on a multi-core system, if I'm on CPU 2 and then I get suspended, let's not say suspended, let's say that I get bumped off the CPU, and then I get scheduled again, the kernel would really like to put me back on that CPU 2 again. And there's a simple reason why. I already have data in that CPU's cache. And so I know that of all the CPUs that may be available, if I get back on the CPU I was on before, it's likely that I'll be able to go faster than if I get put onto a different processor. And not only that, but you can also assign processor affinities to programs so that the kernel will always try to put them on that particular processor. And there are performance benefits or performance impacts for making those kinds of decisions. So there's some interesting stuff you can do with multi-core systems and processor affinities or recording what processor you're on. You have the memory, so we'll talk about that more in the future. That relies heavily on the virtual memory system. Remember that x86, as you know, like most modern processors, uses a page table hierarchy to keep track of the memory. So when we say we record the memory state, we basically just reference the process's page table. And there's one thing we have to change in the kernel control registers to activate a particular page table, and that is the process's memory context. So it's pretty fast compared to how it could be. I'll definitely be talking about that in the future. And then you have all the other allocated resources that the process has open or is holding on to. Because remember, we got to clean that stuff up when the process terminates. And we also kind of need to know if somebody's using file foo, if somebody else wants to come in and delete it. We need to know those kinds of things. Okay, status information. So this is the scheduling details. And you can see that we have all of these kinds of things. I'm just going to throw those up there. Yeah, I'll leave that up there as well. This is basically implementing the state table that we talked about previously. You know, you might have a status field that says what state the process is in, so it's easy to look up. There's also this interesting thing. What is the process's current queue? I don't think that, yeah, so I do have this on the slide here. Status data can be used for specifying pending resource requests for this process, other processes in the same state and priority. One curious characteristic or artifact of the way that our process abstraction works is that a process is always in one queue. If it's ready to run, it's not in a queue blocked on some resource. If it's running, it may be in no queues because it's actually on the CPU, and the kernel, of course, knows that that process is running. But we're always in one queue. And so the status information can keep just one queue pointer for the process because it doesn't need multiple queue pointers. The process is only going to be in one queue. Okay, so that should cover the bulk of information about processes and what we need to record for them as a kernel implementation. Now, I want to talk a little bit about context switches because I've already said a few things, like you probably remember the number 20,000 because I talked about a typical x86 context switch is going to be about 20,000 clocks. So that's time. And if you think about it, that's time we're not doing stuff for the user. So we want to minimize context switches because they do take away time from doing what I call useful work, what the user would like you to be doing. So let's talk a little bit about what goes on here. You have process A and it's running along, and then something happens that gets us into the kernel. It may be a hardware interrupt from a peripheral. It may be a software trap because process A says, I need to make a system call. So it goes ahead and calls into the kernel. So what happens in that interrupt handler or in the trap handler is that the kernel saves all of the state of the process into the control block, okay? And this sounds magical, but it's not that complicated. When the program traps into the kernel, the instruction pointer is saved because you have to know where to go back to. The flags are saved. The stack pointer is saved. And so really all the OS has to do is save the other registers and any other state that it's interested in saving. So it becomes really easy to actually preserve the machine context of the interrupted process. Super easy. Well, actually, I'll show you some of those details in subsequent lectures, okay? Not hard. So now we're inside the kernel. The other reason why we like to save the program state is because the kernel would like to run and use the CPU without trampling on the program state. So now the kernel can do whatever it wants. Okay, so we're in the kernel now doing junk. At the start, we're doing stuff on behalf of process A. Maybe that means process A is now blocked. So it's time to switch to another process B. So you can imagine the scheduler will have run in that little kernel tasks chunk. Okay. So then process B is chosen to run next, and the OS is going to take the machine context from the process control block, and it will restore it. It'll set everything up so that when you leave the kernel, the machine context of process B is restored onto the CPU. So now process B resumes executing, none the wiser that it had not been running on the CPU for some time. Okay, so then we have process B executing. Okay. Yes, and we will definitely be diving into this because as I mentioned, the last thing that you're going to do in the kernel before restoring process B's context is choosing who will be process B. So that's the job of the scheduler. So the last step that occurs there is scheduler execution. Now, context switches take time. Getting into the kernel, getting out of the kernel, obviously that's going to take some time. If you think about what the CPU is doing, the CPU does a rather sophisticated series of steps. It's checking protection levels, it's changing stacks, it's saving information, some of the basic information from the program onto the appropriate stack. And then the OS interrupt handler or trap handler has to save the rest of the information. Okay, so that takes a little time. The kernel has to invoke the scheduler. I mentioned that. So if the scheduler is, well, let's assume that the OS doesn't suck. The scheduler is fast. It's as fast as it can be, but it still takes time. And so we've already identified a few things that take time. Then when we get out of the kernel, we have to restore the CPU state. And of course, the CPU does work on the IRET that goes back to whatever program is being resumed. So that also takes up some time. then oftentimes if we're switching processes, we actually have to change what memory looks like for the new process. So I mentioned the page table hierarchy. Each process has its own description of what memory should look like. So the kernel has to switch from process A's description of memory to process B's description of memory. That also takes time. We have all these things that we have to do. And I might mention as an aside that with Spectre and Meltdown, this is even more complicated because when we switch from process A to the kernel, nowadays we actually, because processors have these basically speculative execution issues that expose kernel state into user space, it's insane to me that this is the case. But since we have these hardware defects, the kernel has to shroud itself as well using the virtual memory system, which means that going into the kernel, we also have to muck with the virtual memory mapping. That also takes time. And that's why people are like, I don't want to do this. I have a computer at home. I don't have to worry about, random malicious users. So I'm not going to employ all the fixes for something like Spectre or Meltdown because I just want my computer to be fast. So there's all this stuff we have to do. Thankfully, you don't have to do it because Pintos takes care of it for you, but I definitely want you to be aware of all these steps. Now, I also mentioned very briefly the translation look-aside buffers. The translation look-aside buffers are part of the memory management unit that allows it to do address translation without actually having to look up the address translations against memory because that's slow. So it keeps it cached on the CPU. The problem is when you switch address mappings, the TLB now contains out-of-date information. So you have to do this thing called a TLB shoot down. You have to basically tell the processor, throw out the information you have in your translation look-aside buffers so that when you switch to the new process, it can populate correctly. Okay, this is especially important. This is actually a source of slowness on multi-core operating systems because if one processor is running a program and it changes the address mapping in a way that it can affect other programs, then that processor has to send TLB shoot down messages to other processors in the system, and that is slow. What can you do? Multi-core. You have to do it. Okay, so this is what I was saying before. The context switch is essential to time multiplexing the processor, but during it, the OS isn't doing anything useful, at least as far as the user is concerned. And so we want to minimize the amount of time the context switch takes, and we also want to minimize how often we do this hideous task. Okay, so these are the important things that we need to think about. You won't have to think about them terribly much in Pintos, but you will have to think about it a little bit because some of the second project has timing-based tests. And by constructing your kernel implementation slowly, incorrectly, will cause tests to fail. And so I think this is an excellent exercise because everything you do in the kernel that makes it faster or leaner as far as resource and time utilization is concerned, it makes everybody better. Like this is the same with like writing good libraries. Writing a good kernel makes all programs better. And so that's an important aspect of OS implementation. And then as far as minimizing the frequency of context switches, this is a characteristic both of application construction and also kernel scheduler construction. We're obviously going to look at it from the perspective of kernel construction, scheduler construction this term. Okay. Last thing that I want to talk about, if anybody has any questions about, and I should just ask, does anybody have any questions about context switches? Go back to this picture. If you do, plop them in the chat or blurt them out. This stuff is really fun. We will be revisiting this multiple times throughout the next few weeks. And so we will dive more deeply into the topic if you have deeper questions that you don't want to necessarily share right now. Okay, last thing to talk about today is these other processes. How do we manage these collections? If you think about the kernel, it's got these collections of processes that we need to manage. Now, most of the time you'll hear us talk about collections of processes as queues. I've got a run queue or a ready queue. I've got a blocked queue. I've got a suspended queue. They aren't always implemented as queues, but they often are. And in fact, the mechanism is pretty clever. I have a lecture that talks about this in the future. It's called an intrusive linked list structure. If you implement a linked list as part of CS11 or CS2 or another class like that, almost always you're used to implementing a node type, and the nodes are linked together, and the nodes have some payload. They have some element that lives inside the node. An intrusive linked list basically flips that upside down so that the elements themselves have the next node pointers. And it's a much more efficient way of doing things. It's also grungy as all get out. And so that's why we only really do it in kernel implementation, because you wouldn't want to do this. I mean, like, maintenance is a serious overhead in application code management. And so we do it the easy to understand way in user applications, but in a kernel where every byte might matter, and you'll see why, kernel stacks are tiny. So, but you know, inside the kernel, we do a lot of these clever systems tricks to maximize the amount of space and minimize the amount of time. I may have said that wrong. Minimize the amount of space, minimize the amount of time that code takes. Okay, so the run queue or ready queue is going to be all the processes that are able to execute. Now, it doesn't have to be a queue, because scheduling needs to be fast. I already talked about that briefly. I might mention as an example, the Linux scheduler, the current default Linux kernel scheduler has a very, well, it's a great marketing name. It's called the Completely Fair Scheduler. And it actually maintains the processes of the Linux system in a tree. And we'll talk about how the Completely Fair Scheduler works in a future lecture. But the way that the CFS works is it always pulls the leftmost child. It always pulls the leftmost leaf out of the tree. So that's super fast. But it's a tree, and so the tree has to be managed in various ways. Okay. Even so, you'll still hear it referred to as the ready queue or the run queue, because it's just the batch of processes that could run if they had a CPU. Okay. When you have processes doing these long-running tasks, you have it read from a file. You have it read from a socket. Well, as an OS implementer, because you're all becoming OS implementers this term, you need to think about the easiest way of managing that process and the fact that it's now blocked. When you read a file, that file resides on some block device. And as the OS, you know what block device that file resides on. And so you can go into the kernel structures and have a queue specific to that device. All the programs that are waiting on data from that specific device. You may have a device blocked queue for every physical disk or every logical disk, or you may have one for every network interface that you have running. Computers can certainly have multiple network interface controllers. It's very common for getting higher parallel data transmission on a high-speed network, because you have these bottlenecks, and the way that you get around a bottleneck oftentimes is to have multiple of them. So if you're waiting for a process, you can have a queue for processes blocked on messages from other processes. So you can actually create quite a few queues in the OS kernel to manage process state. Okay. These processes tend to become unblocked in either interrupt handlers or trap handlers. If a process terminates, you end up getting back into the kernel. Now, the kernel can look at what processes may be waiting on that process in a blocked queue, okay? And as I say on the slide, we need to keep that interrupt handler as short and fast as possible. In fact, a lot of times these things aren't even allowed to allocate memory. We don't even, and there's multiple reasons for that, but it's like they're not allowed to acquire locks. They're not allowed to do hardly anything if you're responding to a hardware interrupt. So, but we can do very simple tasks in these handlers, okay? So we don't have just one collection of block processes. That's the upshot. What we tend to do is have a wait queue for each device that processes can become blocked on, okay? So then, I already kind of ran through this, so I won't spend much time on it. You trap into the kernel. I want to read this file. I want to sleep for 5 seconds. I want to read from this network. The kernel will say, great, I'll set that up on the hardware, and then I'm plopping you in a block queue so that I know you can't run. And when the device tells me it's ready, I know where to look to find out who's interested in the device now being ready. So that's, in a nutshell, how it works. It's very efficient, okay? One of the things that you will do in the second assignment is make a queue for waiting processes, or I should say sleeping processes, okay? So that's like the easy part of project 2 is building a sleep queue so that kernel threads can suspend themselves passively as opposed to doing it actively. So here's a picture, kind of what's going on inside the kernel as far as scheduling is concerned. And there's a number of important places that we're going to be talking about in the last few minutes of this lecture. So you have the ready queue, which funnels into the CPU. If we get an interrupt, we get kicked off, we go back to the ready queue. The process may also terminate. If the process decides to do something slow, we trap back into the kernel, and the kernel will go ahead and put the process into a suitable queue after initializing the operation on behalf of the program. When some hardware interrupt occurs and the process is now able to proceed again, then the kernel will move the process out of the corresponding blocked queue back into the ready queue for execution. Straightforward, right? Easy peasy. If this was all it was, it would be a piece of cake to write OSs. The problem is stuff can interrupt other stuff all the time, and that's where all the complexity comes from. And it's so frustrating sometimes. This is why I like the assignments in the class, because you'll get a taste of that frustration, but in as controlled a manner as possible. Certainly you won't be debugging a priority inversion occurring in a rover that's on Mars, where it takes, 45 minutes to find out if something worked properly or not. I mean, that's a real thing that happened back in the 90s, and I'll hopefully talk about it when we talk about priority scheduling. So process scheduling is a complex topic. We'll spend a couple lectures talking about it, but I want to talk about it at least at a high level today. So there are multiple levels that we can manage the scheduling of processes. I already actually mentioned this earlier in the lecture, that there's the ability to suspend a process so that it's not scheduled at all, and then resume it so that it ends up back in the OS ready queue. So you have long-term scheduling. Long-term scheduling is really all about when do we start jobs? Think about this in the context of a batch processing system. A batch processing system may get 100 jobs, and it may be able to run 5 jobs at a time, or let's say between 2 and 10 jobs. So the long-term scheduler thinks about when to bring new programs into existence. Now, we don't have that in our operating systems because the user is the long-term scheduler. I need to run Fusion 360. I need to run MATLAB. I need to run a web browser. I go double-click the thing and I start the process. So we don't really have long-term scheduling in our typical general-purpose computers at this point. Okay, but yeah, so you have spooling. You can read about that. I'm not going to spend too much time. More history if you're interested in the historical context of our modern operating systems. And so, yeah, the long-term scheduler just picks stuff to start running when it's time. Okay, we'll talk more about this in the future because it's actually quite an interesting problem. It's just one that's not relevant to our modern computer usage patterns. Okay, oh, I guess I do talk about it a little bit. If all the processes in a batch processing system are I/O bound, think about what's heavily utilized and what's not being heavily utilized. If everything's I/O bound, we've got a bunch of stuff in blocked queues, and the CPU is sitting idle. We don't like that because it means that our expensive CPU is not doing anything. Okay. If all the processes are CPU bound, then we're going to have a ready queue that's large, and our peripherals aren't going to be doing anything. The peripherals aren't as expensive typically, but we'd like something to access a peripheral so that something else can run. So the long-term scheduler is trying to achieve this thing called a process mix. We want programs to become periodically I/O bound so that other programs can run, and then the other programs are running, and they can use the CPU. And this kind of minimizes context switching for the computer and maximizes the utilization of all of the components of the computer. Okay, this is unfortunately the problem that we don't talk about anymore. Okay, let's see. Yeah, so this is what I was already talking about. The user will start and stop processes at will based on the user's experience. So the user is the long-term scheduler, if you will. Now, what we do have is this thing called a short-term scheduler, which basically takes from the ready queue and shoves it onto the CPU. Okay. There is another kind of scheduler, which again tends to be relegated to batch processing systems, which is called a medium-term scheduler. This basically deals with mistakes that the long-term scheduler made. A lot of processes are spending time on the CPU and peripherals are underutilized. I'm going to stop scheduling some of the CPU-bound processes to try to achieve a better mix. Or, hey, this process seems to be I/O bound a lot. I'm going to resume scheduling it or resume inclusion so that I can more fully utilize the compute hardware. Okay. So again, we don't tend to have medium-term schedulers in our computers. We pretty much only have the short-term scheduler now because batch mode processing is just not really the thing that we do anymore. Everybody's got it. Like I said, I've got in this room right now, I've got 3 laptops. I've got 4 laptops. I just remembered another one. I've got 2 Raspberry Pis and, like 2 phones as well. 3 phones. I just remembered another one. That, you don't need to worry about batch processing anymore. You just get another computer. So it's not really a thing anymore. All right. Last picture to show you is just the queue diagram with where the schedulers are involved. So you can look at that. I think this makes a lot of sense. So you can study that at your own leisure. Okay. I don't know if anybody has any questions. Feel free to hang out. I will be happy to answer them. What we will do next time is take another dive down into how this picture is affected by the inclusion of kernel threads and user process threads. So I will see you next time.